Hi, welcome to part 2 of our lecture on bipolar junction transistors. Hi, just a note that this is not the usual setting, the background, not the usual setting that I have. It's not the office. I'm currently in Arca's yard in Baguio City. Right? I'm not necessarily promoting, but the ambience here is great, even for recording lectures. So maybe if you want, if you're in Baguio, you can drop by Arca's yard. So it's actually great here. Anyway, so let's talk about bipolar junction transistors. Right. So one way to use a bipolar junction transistor is the common emitter amplifier topology. So this is the basic schematic for a CE amplifier, and the full schematic is shown in the left rather, shown in the left, where you have DC sources, right, and your signal that you want to amplify. So this is the signal that you want to amplify. Uh, Basically, the signal is generally an AC signal, an alternating current signal, which the analysis of which you will learn more in the next, in the part 3 of Triple E 123. So, what is the purpose then of VCC and VIN? VCC here serves as the power for your BJT to activate. V in here is a biasing voltage, right, which the goal is to set a value for V in such that if we go back, you'd want to operate in this region. So a value of V in will uh, the value of V in will be depend will define the value of VBE, which will define where you will operate, what region of the BJT will you operate in. Okay, so that's the purpose of V in right here, the DC voltage V in. So the focus of this lecture is to solve or analyze a BJT circuit, or maybe even design a BJT circuit such that you have a good biasing point, right, where you will operate your amplifier. Right. So the basic common emitter amplifier has this input versus output curve that you see on the right. The input is seen here at the base side, and the output is harnessed at the collector side of your uh, amplifier. Right. So you need to get used to this notation though. So the notation that you see here, where the nodes are defined by the potential. Right. Each of the nodes have their own potential. So we're not talking about voltages here, we're talking about potential. So that's why we want you to master, or maybe even not necessarily master now, but we want you to be able to analyze circuits in terms of their node voltages or node potentials. That's why there's nodal analysis. So your full circuit may look like this, right? But in shorthand, since BJT circuits are very large, the shorthand looks better. Right. So if you're not yet used to this notation or to this shorthand simplified schematic of a BGT circuit, just connect a voltage source to VCC with the value of VCC and connect it to ground. So you get a full uh, view of the circuit, and you will have an easier time analyzing it, right? So okay, so this is the input versus output characteristic of your common emitter amplifier. The input is right here. Right? If the input is very small, there will be no current IB. No current IB, then there's also no current IC. Your transistor is effectively an open circuit. Right? That means if you perform KVL, right, just draw this. If you perform KVL in this loop, you'll have VCC is equal to IL times RL plus Vout. Since IL is 0, that's IC. Your VCC will just be equal to Vout. That's what you see here. It's this region. This is the cutoff region of your transistor amplifier. Now, if VB is very large, just delete that. Right. If VB is very large, okay, if VB or Vin rather is very large, then you're saturating your transistor. At saturation, if VB is very large, IB is very large, IC is also very large, right? But it's less than beta IB, right? IC is less than beta IB. Your transistor is fixed at 0.2 volts. And if you perform KVL, your Vout is equal to 0.2 volts, or VCE saturation in general. So that is at this point right here. At a very large VBE or Vin, your transistor will operate here, and this is your saturation region. Okay. Both of these, cutoff and saturation, are actually useless when we want to amplify a signal. Okay. The best points when you want to operate your amplifier is here, at the sloping region. Because if there's a sloping, okay, there's the part where there's sloping between Vin and Vout. Imagine a small fluctuation. Initially you're at point B. Imagine your Vin fluctuating at C and A. Right? So your signal is fluctuating here, fluctuating towards this one. Okay, so your Vin is basically fluctuating between 0.68 to 0.7 maybe. So that small fluctuation only in the voltage, the effect of which your output voltage has a fluctuation from B to A towards C right here, and fluctuates from 4.5 volts to around 1 volt. So you have to design your Vin. So you need to have a Vin such that you'll be able to operate from a certain point on the sloping. Right? Generally, if you want to have full effect or full amplification, where you ensure that you won't enter the saturation region and the cutoff region, you would want to design a Vin such that your Vout is operating initially at around the point B, which is around half of 2.5 volts. Generally, it's VCC over 2. At that point, you can operate your amplifier to its fullest. Right? So, the problem is, okay, if you look at this circuit, from the full circuit on the left, see that V in here is a separate battery that you want to connect to your base. However, that won't be practical because in reality, large amplifiers, even operation amplifiers, have multiple CE stages or amplifier stages. There's a lot of them, basically, connected to each other. Not just a CE amplifier, there are others. There are other topologies that we connect with each other with different properties that we want. Okay, but all of them will have a battery connected to the base. That's not practical. Okay. Ideally, we want a single battery powering all of them up. How do we do that? That's where your bias circuit comes in. An example of a bias circuit is a fixed bias circuit where you directly connect the VCC to the base via a resistor RB. Right. So let's try to analyze this circuit. Find Vout. Right. Find Vout. I'd prefer nodal analysis. Right. Assume forward active if you're not yet uh, comfortable with solving this circuit. Transform it to an equivalent circuit. So the equivalent circuit will look like this. Sorry, maybe I'll just clean this. This should be VBE. Okay, and this is beta IB. Oops, sorry. Let me just, there you go. Those are the answers, right? RC, RB here. Okay, so you perform nodal analysis on this circuit, right? And as you can see, it's just easier compared to the examples that we had using nodal analysis. Uh, you have two nodes, right, of interest. Since the ground is already defined, those two nodes will be used. Let this be VB, and let this be VA. Right? Automatically, VA is equal to VCC, right? Since it's connected to VCC right here, ideally. Okay, so VA is equal to VCC. Next is VB. So with VBE connected here, the potential at this node is already VBE. And with that, we can solve for IB. Right? IB, quite simply, right? IB here is equal to VCC minus VBE divided by RB. Okay? And we have IC, which is equal to beta IB. Okay? So IC, based on this, is equal to beta times VCC minus VBE over RB. Now we will now be able to solve for V out. Right. So let me just clean this a little bit. Yeah, it's already ruined. Anyway, V out is right here. Right. How do you solve for V out? You perform nodal analysis at the resistor RC. So with that, resistor RC, the potential difference at the resistor RC is VCC minus V out divided by RC, and the current across RC is equal to IC, which we got an expression earlier, as you can see here. So VCC minus V out over RC is equal to IC. Therefore, V out is equal to IC RC. Sorry, V out is equal to VCC minus IC times RC. Right. And IC can be expressed in terms of beta. So it's VCC minus beta RC over RB. Sorry, RB times VCC minus VB. There you go. Right. And this is your this is the V out as a function of all the other parameters in the circuit. Okay. And this is how you solve it using nodal analysis, right? So let me just clear the slide. Okay. So when using KVL and KCL, we get similar results actually. Okay. So you see here. Okay. I prefer nodal analysis, of course. It's a much easier approach compared to KVL and KCL, especially when you have a simplified notation such as this. Right? So it all depends on what you prefer though. So just practice and you'll get the hang of it on what you're more comfortable with. Okay. Another example of biasing circuit is connecting an emitter resistance, and you have an emitter stabilized bias circuit. Okay? And in a similar way, we can express V out as a function of all the other parameters given in the circuit. Okay? And you can do that using nodal analysis. So if you're not comfortable with it yet, then you have to draw the circuit with its equivalent like this. There you go. So this is your circuit using nodal analysis. You have two nodes with three or more branches connected to them. You have let this be VA and let this be equal to VB. Okay? So you have an emitter stabilized bias circuit. So I'll leave the analysis to you on your own. All right? And using KVL and KCL, your V out is expressed this way. Okay? And your IB can be expressed in this way. And all of these are given parameters in the circuit. We can solve for V out. Okay? Another example, one that is more flexible compared to the others is the voltage divider bias circuit, where you have a voltage divider that is connected at the base, right here. So using this voltage divider bias circuit, we give more flexibility towards setting a voltage here, the potential here, VB, so that we're able to uh, select a V out more flexibly. Is that even a word? I don't know. Anyway, you will be able to select a potential or a bias point so that you can control V out. I remember when we were designing uh, an amplifier circuit for our design problem, some people would use a potentiometer to bias a CE stage. So you can do that actually. Just uh, uh, turn the potentiometer to an optimum point such that V out is at the half of VCC. Right? And that it also works. Right? So let's look at how we can analyze this circuit using a voltage divider. Uh, Consider first this connection here on the right side of your screen, where we have a voltage divider connected to VCC. We can split this circuit. Okay? Let's remove the transistor first, and then look at the Thevenin equivalent seen at this part of your circuit. Okay, the Thevenin equivalent, okay, at that base, let me just clean the screen. The Thevenin equivalent is your VTH at this point, assuming the transistor is disconnected. It's quite easily a voltage division between R2 and R1, and that's this equation here. Your Thevenin resistance is you suppress your input VCC here, so that means you will connect this to ground. That makes R1 parallel to R2, and your Thevenin resistance is equal to this one. Okay? And with that, we can connect that circuit to your uh, common emitter amplifier topology, and you'll end up with this simplified circuit on the left, and we can now analyze V out as such. Okay? So using KVL and KCL, well, you can analyze this. But again, I prefer nodal analysis. And if you're not yet comfortable with this notation on the left-hand side of the screen, I suggest you convert the circuit to the equivalent circuit of the transistor. So that's what you see on the screen now on the right. There you go. And with this, you only have one node of interest here. We'll call it VB, which is the potential at the base. Right. You do that, you'll still get the same answer as if you will solve the circuit using KVL and KCL. So again, it depends on what you are comfortable with. So find a comfort zone, right? And do that by you can do that by practicing a lot. Okay. So last example for a biasing circuit is a DC bias with a voltage feedback. It's called a feedback because normally, or not normally, the output is measured here, as you can see, and it is being fed back to the base. That's why it's a DC bias with voltage feedback. And again, to analyze this, connect the equivalent circuit. An equivalent circuit of that would be this one. So IB is here, beta IB is here, this is VBE, normally 0.7 volts. RE is equal, just RE, this is just RE, so R1, and this is equal to RB. And you only have, no, not only have, you have two nodes of interest here now. You have this node and this node. Okay, so you have two equations with two unknowns. Okay, that's easier, right, compared to what we have given you as an example for nodal analysis. And using KVL and KCL, you'll get these results. So I'll just give it to you to verify if they are correct. I'm not really comfortable with using KVL and KCL. I'd rather use nodal analysis. Okay, so let's have an example, not an exercise. So I'll help you solve this problem. Right. So the task is to find IB, IC, VCE, VC, VB, and VE. We'll solve this using nodal analysis. So nodal analysis, the first step, if you're not comfortable, is to convert it to an equivalent circuit. Right. For now, I have no space here on the screen. I won't convert it to an equivalent circuit, but I already know that at this point here, that is the potential VB. Okay? And that's the only potential that we don't know. Since we have connected this, okay, by default, if it's forward active, already assume that the voltage drop here is 0.7 volts. Okay? And since the voltage drop here is fixed at 0.7 volts, then VB is at 0.7 volts. We can now solve for IB, since IB is the current flowing through this 470 kilo ohm resistance. Okay, so IB is equal to 16 right here minus VB, which is 0.7. That's 15.3 volts divided by 470 kilo ohms. That's how you solve for IB. Next step is to verify if it's greater than 0. So we already know it's greater than 0. This is greater than 0. That means your transistor is not at cutoff. Now we solve for IC. That's equal to beta IB, and beta is given to be 90. So beta IB, right, so that's just 90 times 15.3 divided by 470k. Right. And the next step is to solve for VC. Since we already have IC, we can solve for VC using nodal analysis here. So VCC, which is 16, minus VC divided by IC is equal to, divided by 2.7k rather, which is the resistance, is equal to the current IC. You can now solve for VC, which is equal to 16 minus 2.7k times IC. Okay, and we can solve for VC that way. VE is directly connected to ground, therefore it's 0, and VCE is equal to VC minus VE. Okay, and so VCE is equal to VC minus VE. You have to verify if this is greater than VCE saturation. And normally VCE sat is set at 0.2 volts. So if you have verified that VCE is greater than VCE sat, then we know that the transistor is in the forward active region, operating in the forward active region. Okay. I'll leave it to you to calculate these. I don't have a calculator with me, so I'll leave it to you. So verify if we're correct. Okay. Another example is this one. So you're given the potential at each node and IC being 2 milliamperes. Assuming we are in the forward active region, what should be the value of RB, RC, RE such that we are in the forward active region? Okay, and find the other parameters VCE and VB. Quite simply, you can already solve for VCE here, since the potential difference at the collector and the emitter can be directly solved given the potential at the collector and the potential at the emitter. So VCE is quite simply 7.6 minus 2.4, which is equal to 5.2 volts. Excuse me. With IC equal to 2 milliamperes, IB can be solved. So IB is equal to IC divided by beta, where beta is equal to 80. That's 2 milliamperes divided by 80. That's equal to, 25 microamperes. Right? So given that, okay, and since we're in the forward active region, we already know that the potential difference between the base and the emitter is 0.7 volts. With that, we can solve for VB. VB is equal to 2.4 plus 0.7 equal to 3.1 volts. We can solve for RB in this way, right? By nodal analysis here, 12 minus 3.1 volts divided by RB is equal to the current IB. It's passing through here. And we can solve for RB. RC can also be solved immediately. Since IC is 2 milliamperes, we can solve for RC. The potential difference is 12 minus 7.6 divided by RC is equal to 2 milliamperes. We can now solve for RC. And finally, RE can be solved here. Note that by KCL, IE here, the current at the emitter, is equal to IC plus IB. There you go. So IC plus IB. And if it's in the forward active region, you can simplify this, express it in terms of IB. There you go. Okay. And we can now solve for RE using the potential difference at RE. So this is 2.4 volts divided by RE. That's equal to IE. Okay. And you will now get the values of the resistances such that your transistor is operating at the forward active region. And that's how you design a transistor circuit. Okay, another example. Number 1, find the different values or parameters required here, and you have a voltage divider circuit, voltage divider bias circuit. One step is to convert this first to a Thevenin equivalent. If you're not comfortable with that, that's fine. Right? So that's fine. If you're not comfortable with it, then you can just use nodal analysis. And in this case, this is your unknown node. Let's call it VB. And there are 4 branches connected to VB. Current going here, here, out here, and out here. Right? So, okay, since it's in the forward active region, your VBE is at a voltage drop of 0.7 volts. Right? So 0.7 volts, we can set up the nodal analysis equation to solve for VB. So going up here, the current there is VB minus 16 divided by 62K. Going down, it's VB, okay? VB minus 0 over 9.1K. Going down here, that's equal to VB minus 0.7. That is the potential here at VE, since there's a potential difference of 0.7 volts here, divided by 0.68K. Right, and finally, you have a current going up here. Right, since you're in the forward active region, that current is negative of IC. Right? And IC at the forward active region is beta times IB. Right? So IB is flowing here by KCL. If you perform KCL at this node, IB can be solved as a function of VB. So IB is equal to the negative of the sum going out of this of the currents defined as going out of this node. So IB is equal to negative of this, that is 16 minus VB over 62K, and you have the negative of this current here minus VB over 9.1K. So you have 2 equations with 2 unknowns, and you can solve for VB and IB. And once you have solved for VB, you can solve for IC. So IC is equal to beta IB. You will be able to solve for IB once you have plugged in the coefficients of the 2 equations with 2 unknowns in your calculator. You can solve for VC and VE. by using nodal analysis. VC can be solved by knowing IC. So that's 16 minus VC divided by 3.9K. That's equal to IC. Okay. VE can be solved also. Once you get VB, VE is quite simply VB minus 0.7. And finally, well, you'll be able to solve for VB once you have solved for the system of equation. So VCE is quite simply VCE minus VE. Okay. The next question is determine the saturation current. At what value of IC will the circuit saturate? So basically, since we're trying to determine IC saturation, you assume that the circuit is in saturation. The potential difference between VC and VE is 0.2 volts. So note that during saturation, IC not necessarily equal, sorry. During saturation, IC is less than beta times IB. Okay. But at exactly, right, there's a point where IC is still equal to beta IB, but VCE is already at 0.2 volts. Okay. So we let IC be equal to beta IB in this case. Okay. So how do we solve for IC sat? So in this case, where IC is equal to beta IB and VC is equal to 0.2, IC is equal to beta IB. If we perform KVL in the outer loop, right here, we have a voltage source here. Okay. If we perform KVL, that's VCC minus 3.9K times IC, okay, minus 0.2 minus 0.68K times IE, okay, equal to 0, where IE is equal to IC plus IB. Okay. With that, we will now be able to solve for IC saturation. If you solve for IC in this equation, you will be able to determine the saturation current IC. Okay. And I'll leave it to you to solve for the values, the calculated values. I don't have a calculator with me again. Okay. Last example. Okay. Determine the range of RB that will operate the transistor in saturation. So since we're going to assume now that the circuit is in saturation, by default, okay, this should be 0.2 volts. Right? So let's say we're at the boundary of saturation and forward active. That means we want to get IC saturation first. Okay? So IC saturation can be solved in the same way as this exercise. Okay? So that means IC is still beta IB. Right? And since we're in the saturation region, the voltage drop at the base emitter junction is 0.7 volts. Right? With that, we're all set. Right? So first, solve for IC. So IC saturation. If you perform KVL in this loop again, that's VCC minus 2.7K times beta IB, right? Minus 0.2 volts minus 680 times beta plus 1 IB, right? Since IE here, the current here, is equal to beta plus 1 times IB, and that's equal to 0. With this, we can now solve for IB. IB is equal to something, right? Since given VCC, given beta, we can solve for IB. Right? So after we solve for IB, we can now solve for RB. Right? RB, if you perform nodal analysis here, right? Or if we don't want nodal analysis, we can perform KVL in this loop. The KVL in this loop is starting at VCC. It's VCC minus RB IB, right? Minus 0.7 minus 680 times beta plus 1 IB. So once you have solved for IB, that's equal to 0. Once you have solved for IB, you can solve for RB in this case. Right? And the value of RB that you'll get here will be the maximum value of RB. Okay? So you just reduce RB. Okay? If RB is less than RB max, okay, you're guaranteed here that the transistor will operate in the saturation region. If RB is less than RB max, then IB would increase. Okay? Since IC cannot operate less than or greater than IC sat, okay? Since IB increases, know that if we're in the forward active region, if IB increases, IC increases. But since we're in the saturation region already, IC cannot increase anymore. IC cannot increase greater than IC saturation. That can never happen. So if we set RB less than RB max, we are sure that the transistor will always operate in the saturation region. And that's how you design the circuit such that it will operate in the saturation region. Okay, and that's the end of all the examples. Right. So just an FYI for everyone, there's two other topologies that we use for BJTs. One is the common base amplifier. So the common base amplifier has this input versus output curve, right? So it's called common base since we have grounded the base and harness V out at the collector where our input is at the emitter side. So this is still an amplifier, right? And it has a positive slope here, right, as compared to your common emitter. The common emitter has a negative slope. If you recall, let me just try to draw the curve. The curve looks like this for a common emitter amplifier. Right? Since the slope of the common emitter amplifier is negative, then the gain is also negative. Right? Since we're talking about V out over V in, right? Or if we're talking about the gain, we're actually getting the change of V out with respect to V in. Okay? The slope here is negative, therefore this is negative for a CE amplifier. But for a common base amplifier, you have a positive slope, therefore the gain, change in V out divided by V in, is greater than 0 for a common base amplifier. Right? So the other parts of your common base amplifier curve here is the cutoff. Here is the saturation. And in this region is your forward active region. And again, you have to design the circuit, right? Properly bias the circuit such that you will operate at half of VCC. And that's for your common base amplifier. Another one, if you have a common emitter and a common base, of course, there's a common collector amplifier. And the best thing about a common collector amplifier is the slope of this amplification here is approximately equal to 1. Okay? That means, and there are certain properties why it's not amplifying, right? V in is equal to V out. So why do we still use it as an amplifier? There are certain properties of a common collector amplifier that is advantageous when we use it, right? Compared to a common base and a common emitter amplifier. And I believe we'll talk about that in the 10th module, lecture 10. Right? So, sorry, lecture 9 rather. We'll talk about it in lecture 9. So there are properties of a common collector amplifier that we want, right? And its properties are better compared to common base and your common emitter. Right? And bottom line, the gain is approximately 1. It's also called a voltage follower. Just a note, in this region, your circuit is still in the forward active region. This is cut off. And this is when your amplifier is saturated. Okay? And that's the end of this module. So I hope you learned something new here. And if you have any questions, Of course, again, if you have any questions or comments, do not hesitate to leave them in the comment section below. Thank you for listening. And if you find yourself in Baguio City, uh, you can visit Arca's Yard. It's very cozy here. All right, thank you for listening. See you next meeting.